So our next talk in this session will give Layth Muhsin Alabdulsada. He is from Al-Qadisiyah University in Iraq. The title of the talk will be Hopf Rinow, theorem of sub-Finslerian geometry. So, Layth, my friend, please, can start.
Thank you. Thank you very much, Dr. Omram. And I want to take the opportunity to thank the organizer for inviting me and giving me this opportunity to share with you my results. This is about sub-Finslerian geometry. It is new generalizations of sub-Riemannian generalization, and this, some of you may be familiar, some are not, with the Finslerian geometry. As you know, Finslerian geometry depends on the metric. That metric defined as a function from the whole tangent bundle to the positive R. And here in this setting, sub-Finslerian, the sub-Finslerian geometry means that the metric defined only on the subbundle from the tangent bundle. And so the Hopf Rinow theorem, it's already proved and stayed in the Riemannian settings and in Finslerian settings, and also some of them mention it in sub-Riemannian. But in sub-Finslerian, this is the first version. Nobody mentioned this proof yet. So just a brief introduction about Hopf Rinow theorem. This theorem, it's basic theorem in complete Riemannian and Finslerian manifolds, which connect the completeness properties with the compactness and the exponential map as well. And consequences says that any 2 points of a manifold can be connected by the length minimizing geodesic. So this is a joint work with my supervisor from, he was my supervisor in my PhD. I graduated from University of Debrecen in Hungary. He is busy. Unfortunately, he didn't get the opportunity to attend this conference. So the settings for this, first of all, we have a manifold, and this manifold should be n-dimensional connected manifold with the sub-Finslerian structure on this manifold. And this triple, it is the subbundle, we denoted by D. And this is, I don't know, I forget, this is gamma, or this is not gamma. It is delta, or this small. Anyway, this notation, take from D to the
Sigma,
Tm.
you mean?
Yeah, sigma. It is, and this function, we have that f from delta from the subbundle to the R, where D here we keep some tilde on it. It means that we remove the zero section, and then we call this function a sub-Finslerian metric if the following properties are satisfied. The first one, it is the positive definites. That means that the function from the position, we have position here, or the point at the manifold, and V in the vector on the subbundle, and this function should be positive. This is greater than 0. Also, the regularity, that means that F is smooth, and positive homogeneity, which means that it is satisfying this condition here. And the last condition, the Hessian matrix F square with respect to the vector variable, it is positive definite. Then if this condition are satisfied, we can say that a sub-Finslerian manifold, it is manifold M with the subbundle with a sub-Finslerian metric. And this is a smooth manifold, as I mentioned, is endowed with the sub-Finslerian structure. Just let me, yeah, now maybe it's better. And then This is some notation we need. That, for example, here the corresponding indicatrix we defined as a set of the vector v, and v is it is in the subbundle such that the Finslerian metric equal 1. And from now on, we will suppose that D it is sub bundle from Tm, and this function here it is, or this map is inclusion map, and then we will call the F it is just sub-Finslerian metric. And as in Finslerian and Riemannian, we define the length here, it's the setting for the length is a bit different. First of all, we have this distribution D, and this is, we call it horizontal distribution. It's not meaning that it is horizontal, it's just a name, horizontal. If we have a curve from 0t to m, we call this curve a horizontal, or some books they call it admissible, if the derivative of this curve with respect to t belong to the distribution d at the point gamma of t for any t in this interval. Or in other words, we can say that the gamma of t it is tangent to d. Then we can say the length is a piecewise smooth horizontal. It is not just smooth, it is piecewise smooth horizontal curve gamma, defined as the integration from 0 to t of the Finslerian metric for the derivative of the curve gamma of t. Then if we have a length, we can induce a sub-Finslerian distance, and this distance we can define it as the infimum of the length of gamma. Here also we call the absolutely continuous horizontal curve between 2 points x and y realizes the distance x and dx and y is called the minimizing geodesic between x and y. In distribution, when we have a distribution, not always any 2 points can be connected by a length. So that's one of the scientific chows. He said that some of them are bracket generating. When we have, so in this research, we are talking about only when the distribution is bracket generating. So bracket generating means that any local frame xi of the distribution together with all its iteratedly bracket span the whole tangent space. So when the case that it is not bracket generating, which is the second option here, so we cannot span the whole tangent space. That's why we suppose that, or we assume all of our distribution here, it's bracket generating. And Chaus says that in 1939, if the distribution is bracket generating, then on a connected manifold, then any 2 points in this distribution can be joined by horizontal path. To prove our theorem, which is the main theorem here, it's the Hopf Rinow theorem, we have to construct some facts relating to this new setting. So first of all, the legend transformation of the sub-Finslerian manifold. We generalize this. So first of all, we have the distribution, or you can call it co-distribution, on the cotangent bundle, and this cotangent bundle defined as the set of a point P, and P should be linear. Then we have the sub-Lagrangian function. We define it as the all equal the half of the square of f, and f here, as you know, it is Finslerian metric, sub-Finslerian metric. Then the fiber derivative of all defines the map. This map defined here from D to D star, D in the tangent bundle and D star in the cotangent bundle. We call it the legend transformation of the sublagrangian, and it defined locally and globally by these two, expressions. Then, after we define the sublagrangian and its legend transformation, we come to define the subhamiltonian and its legend transformation. First of all, we have this H equal, or it is a function from D star to R, and then this map here, it is the legend transformation of the subhamiltonian, which is given by, or it's hold that's this globally and this is locally. In other words, that we can define sub-Finslerian metric, we can get, as we define sub-Finslerian metric in D, we can have a sub-Finslerian metric defined on D star by this equation that F star of the point P here it's a covector, which is equal to the supremum of P of W, and W here it is V over F of X over V. Moreover, this function defined in the following, that's from tilde D star to R, have the same properties as mentioned in the beginning in the first definition. Therefore, we have this, that F star of P equal to the F of V. So by the legend transformation, we can say that this is true. And H equal to the half of F star, square of F star. Now, we came to define or to construct the sub-Finslerian bundle to introduce or to define a subhamiltonian formalism that we need to prove this theorem. So first of all, we suppose that we have the cotangent, or we have the distribution on the cotangent and tau with a manifold. And tau here is just a projection from D star to M, which is a covector subbundle of rank K. You know, this distribution, it has rank K different from the dimension of the manifold. And then the pullback bundle, which is defined by tau star of tau, D star times D star, and PR1, which is given here, and with a DR of tau by tau, this is the sub-Finslerian bundle over D star. And after that, when we can introduce we can introduce a Riemannian metric, and this Riemannian by the sub-Hamiltonian given by this globally it's given by this formula, and locally it's given here. And now the sub-Finslerian bundle allow K covector, which is the rank of the distribution, K vector covectors field, which is given by x1 to xk, which is orthonormal frame with respect to the induced Riemannian metric that's given above. And notice that xi of P, it is a covector that depends on the position and a direction P in the on the co-distribution, since we are in the Finslerian, because you know the difference between Riemannian and Finslerian, that Riemannian depends only on the point on the manifold, but for Finslerian depend on the point and the direction on the distribution, that it is subspace or subbundle from the cotangent bundle. And also here we got this formula that x of the position here, or the point x in the manifold, and p is the covector, given by half of the summation jij star pi pj. And this can be written in this formula, which is more familiar in sub-Riemannian and sub-Finslerian, that and we also prove that this is homogeneous of degree 2. And from this formula 2 here, we can generate sub-Hamiltonian differential equation, which is which we can call them as a normal Jones equation that we will use later for prove our theorem. And now After we prove this or introduce this sub-Finslerian bundle and the formalism of the sub-Hamiltonian, we can define the xi of t equal to the x of t, which is the point, and the covector p of t. And we call this normal extremial. And because we have in our distribution, we have two things, that one of them is normal extremial and abnormal extremial that don't satisfy this these conditions, and or don't satisfy the sub-Hamiltonian equation that we just presented above. A normal Finslerian geodesic, which is just x of t, this is the point, equal to the tau the projection, xi of t, which is just the above, this is belong to the manifold. We call it simply the normal geodesic. Now we can generate the following form of the system of differential equation that's given by these two formulas here. Now our theorem. Before we start our theorem, we need the exponential map, of course. So for that, let's the domain here, subspace from the distribution, we will have two exponential map. One of them defined on the tangent on the distribution, that's sub-bundle from the tangent bundle, and the other one defined on the co-distribution, that is sub-bundle from the cotangent bundle. So here, this domain defined as the set of V belonging this notation here, and xi is defined on the interval 0, 1, where V here it is the sub-Lagrangian transformation on the sub-Hamiltonian. And now we can define the exponential map, that it is from tangent bundle, but it is restricted to the distribution, such that this here it is this domain, it is just the subspace from the distribution. And the other one, when we have a domain on the co-distribution, and this domain defined as a P here is a covector, we can define the sub-Hamiltonian equation, or sub-Hamiltonian exponential, which is defined from the cotangent bundle that restricted to the co-distribution to the manifold. And by the Legend transformation, we can find that exponential of V equal to the exponential defined on the tangent bundle, and this exponential defined on the cotangent. So after what we introduced, we proved that if we have any point in the Finslerian manifold, sub-Finslerian manifold, and the ball, closed ball, that the center is X and we have a radius R, is a compact ball for some R, positive R, then for any Y, another point in this ball, there is a minimizing geodesic from X to Y, such that, which mean that the distance between these 2 points, it is the minimum of the length of the set of the length, and this gamma, for the gamma and this gamma, it is a horizontal path between these 2 points, such that gamma of 0, it is the initial point, and gamma of t, capital T, is the end point. Now, since we know that in Finslerian, we don't have just complete manifold. We have forward complete and forward geodesically complete, and as introduced by Bao Chen Shen book. So the definition for if we have a sub-Finslerian manifold, we call it a forward complete if every forward quasi-sequence converges. And it is forward geodesically complete if any geodesic, gamma of T, parameterized to have constant speed, can be extended to geodesic for all T. So before T, it is from 0 to T, capital T. Now we can say that T from 0 to the infinity. And a subset is said to be a subset in this Finslerian manifold is called forward bounded if it's contained in some forward metric ball. Now our theorem is ready. If we have a connected subfinstelian manifold where D is a bracket generating, this condition is very important, then the following conditions are equivalent. First of all, the metric here, MD, is a forward complete. Then the subfinstelian manifold MDF is forward geodesically complete. Then this domain, it is equal to the cotangent, sorry, not cotangent, it is co-distribution subbundle of the cotangent. Additionally, this exponential map, it is onto if there is no strictly abnormal minimizer. The last condition, every closed and forward bounded subset of the metric space is compact. Furthermore, for any 2 points in the manifold, there exists a minimizing geodesic gamma joining these 2 points, which means the length of this geodesic equal to the distance between these 2 points. So first of all, we prove this theorem. I can give you some hints about it. First of all, we prove that this metric, it is the sequences here is converges, and then we suppose that here that we cannot extend T from zero capital T to 0 infinity, which we got that contraction. This it cannot be happen. So it means that this subfinstelian manifold is a forward geodesically. And then by using the equation that I introduced there about the formalism of sub-Hamiltonian, I prove that this condition here, first of all, it is true. And then we prove that the exponential map, it is surjective. And also, since we got this, we can prove that this closed and forward bounded subset of MD is compact. And since we prove in the proposition that I showed before the exponential map section that any 2 points we can connect it by geodesic or by geodesic joining these 2 points. The references that we use here, first of all, Agrachev, Bariali, and Boscan, a comprehensive introduction to the sub-Riemannian geometry. They prove some points of this theorem, but separately, not as a one package of theorem, but in the sub-Riemannian geometry settings, not in sub-Finslerian. And Bauch and Shen prove this theorem in Finslerian settings. Also, I use this paper with my supervisor in my PhD studies on the connection of sub-Finslerian geometry, which is very good paper. And this paper now, this result is already putting in the archive in this link. Also, I use this paper, sub-Riemannian geometry, for Klein and Ching, and chose that prove this theorem that any two, if we have a bracket generating, then any 2 points that can be joining by geodesic. And also this geodesic of sub-Finslerian geometry, I use it, and Citrax and Rupert about sub-Riemannian geometry. Also, this paper, it is old paper, but they use some points how to prove the Hopf Rinow theorem, but also he didn't mention it in details. Thank you very much for your attention.